Maybe I need tomorrow. Oh, let me get tomorrow. Oh, yeah. You go out, come back in class. That's it.
Get to sleep in. All right, let's get started. So we're back into induction motors. It's been a bit. So we'll just go through really quickly the kind of the predecessors, where an induction machine is very similar to a stator machine. In fact, I don't even really talk about the stator windings because the stator windings on a synchronous machine are pretty much the same as an induction machine. The difference between the induction machine and this, yes, sir. Oh, I didn't plug it in. Sorry. Only done this 500 times. You would think I would remember. All right, hopefully it's working. There, we're back in business. So the induction machine, the rotor on it, we're going to discuss briefly the other type, but the main one we're going to talk about is the squirrel cage induction rotor. And the squirrel cage induction rotor or induction machine is one where we have no external connection to the outside world. What is on the rotor circuit gets there because of induction. That magnetic field that is on the stator circuit is going to cut the windings on the rotor circuit, and then you're going to induce currents and voltages and whatever else you need to go ahead and create the magnetic fields or the currents that you need on the secondary side. So is there another device that we've studied this semester that there is no physical or no electrical connection between the stationary side and the rotating side, or from one side to another? Have we covered a device that has, you provide power, let's say we're providing power into a box, and then we can get power out of this box, but inside the box, the power in and the power out physically don't come in a connection with each other. They don't touch each other in any way, shape, or form. Was there a device that we discussed? Transformer. Isn't a transformer, we have a primary winding and a secondary winding, and all the energy that goes from the primary to the secondary is transferred magnetically through the core of the transformer. So an induction machine is operating just like a transformer. The difference is that that secondary side can rotate. So when we talk about a rapidly changing magnetic field, the deep VDT, that has everything to do with the fact that you have a stationary set of windings. So the frequency of a transformer on both the primary and the secondary side is going to be exactly the same. 60 hertz in means 60 hertz out. With the induction machine, we don't have that same frequency, right? Because we have some rotation. And so that's why we talked about the rotational frequency on the stator, on the rotor, which could be determined by taking the slip and multiplying by the applied electrical frequency. So just like what we did for a transformer, we can do a lot of the similar things for an induction machine, even to the point where we'll cheat and we'll be lazy and we'll use the equivalent circuit of a transformer and tweak it just a wee bit. Let's see, let's stop. I guess I can move that out of the way. So what we have is a transformer, right? You can see that I have the winding on the primary side, losses. I have some leakage losses. I have some core losses, and I have some magnetizing losses. This is exactly the same as that primary winding model. And it's so close to being the same, there's actually a transformer in here. And we need that transformer because there is no electrical connection between the two. Remember the isolation that transformer provides, we actually get isolation between both sides. And this is the secondary side of the transformer where we have that leakage reactance term. And we also have our winding resistance or equivalent winding resistance. What's different about the secondary of the transformer in here is this. This is a short circuit. And that's how the winding on the rotor is constructed. It's not left as an open circuit. It is actually short circuited. Okay. So we can use our equivalent transformer circuit and just go ahead and convert it to our induction machine. But now we're going to go ahead and short it out. So everything is the same. What's harder, though, about an induction machine is this. That turns ratio is A effective. Why do you think it's an effective turns ratio? Anybody want to hazard a guess? Think about how you get a voltage developed on the secondary of our transformer. Where does that voltage come from? Comes from the number of windings, right? The number of turns. So that's not going to really change, right? Once the machine's built, we're not going to change that. But it also has an impact on how fast that flux is changing. So that A effective is going to change because as the rotor picks up speed, it's going to have a different effective impedance because now your voltage on your secondary side is going to look different depending if it's running at 1,000 RPM or 100 RPM. You're going to get a different characteristic. So we don't even actually define this as a turns ratio. We just leave it as A effective. And actually, we're going to go ahead and come up with some new parameters over here, JXR and RR, that kind of simplify things a little bit. But what's important is all the electrical power in the circuit has to be consumed or shown as being consumed by the equivalent circuit. Does everybody understand what I'm saying there? You're providing a voltage and a current to an induction. We'll mainly talk about induction motors. All that voltage and current, the power that goes in, has to be accounted for in this particular model. So what does an induction motor do? It converts electrical energy to mechanical energy. So the output power in torque or foot-pounds, whatever you want to call it, that's actually going to be captured in here. So we actually have R sub R. That's not only the winding resistance, but it also has to be the equivalent of the load that is on that particular machine. Okay. So not X sub R. Why doesn't this have to be indicative of the load that's on the secondary of that circuit here? Can I pick on some of my mechanical engineering friends? All the mechanical engineering friends are going to keep their heads down if they don't answer the question. What does the power output of a motor? What is that? It's in watts. Is there any borrowed power that goes out on the shaft? Does it go out and then come back on the shaft? No. So mechanical power doesn't have to worry about reactive power, that sine wave that goes negative part and take back in. It's just spinning, and that power that gets sent out is gone. It ain't coming back. So we don't have to worry about reactive power because that power is never coming back in a motor application. So we talked a little bit about this speed change, which makes things very difficult for us. It's hard to come up with an equivalent circuit because the speed is changing. But we can talk about things as a function of a set or specific point on the machine. And we know that that specific point can either be running at full speed or synchronous speed or running at no speed, because getting between 0 speed to 100% speed is going to be, it's going to take whatever characteristics it's going to be. But the reality of it is that we need to pick one of those two so we don't have to worry about the transformer's effective turns ratio. Almost got to sneeze, so might have to stop for a moment. But anyway, we don't want to use the one at full speed or 100% because there's no voltage, right? So all of our characteristics are going to be based on using our block rotor values and then adjusting them based on slip. When a machine is not slipping at all, when it's running at synchronous speed, then there's no voltage on the secondary side. So S is equal to 0. And if I take a block rotor voltage, then I have S times ER0 is equal to that secondary voltage. Similarly, when I'm under blocked rotor conditions, I'm going to have the exact highest voltage that I can see because the dφdt is at its maximum. So when a motor, an induction machine, is not running or starting up, we call that blocked rotor conditions. And that's when it's going to have the highest voltage, and also it's going to have the highest current when the machine starts, because this voltage here is at its peak. All right. So we did that for frequency. We talked about that for frequency. Now we know that an inductor, and this is an AC circuits one, we can solve for the reactance of an inductor based on omega L, and omega is 2 pi F times L. Well, the frequency is back in here. And that frequency, again, is going to change based on the slip. So I'm going to modify my frequency, if you will, or modify my impedance by taking my block rotor impedance, XR0. I can measure the block rotor impedance. I can energize the motor, and we'll do that. We'll actually do tests at some point where we lock the rotor in position and we verify that, or we can calculate what that impedance is. And then I vary that based on the slip. So at full slip, I'm going to have the full reactance over there. When I'm at very little slip, the voltage drop across my inductor is going to be almost negligible because there's no current flow through there. So again, I've just taken my voltage and moved it over with a slip. And now I've taken my reactance and moved it over, where I've been able to represent that with a slip. So here's my equivalent circuit. Getting rid of the A effective, I've got a voltage here in the secondary, and that voltage is going to be a function of slip. And I also have a reactance that is a function of that slip value as well. You will notice that R sub R is not slip based. That's going to be based on the power output and a couple of other factors. So we can calculate the rotor current. So IR, the current flowing through the rotor. And again, that rotor current has to be the one that provides the power as well. So that's ER divided by the sum of the impedances. Now I'm going to substitute in my value of block rotor voltage and block rotor reactance. So I have my S terms in there. Now I'm going to divide by S. And now what I've done is I've got this term here that is my rotor resistance divided by S. And again, that value makes a big difference because that equivalent circuit that I have on the secondary side, it should be representative of what's happening in terms of the machine running at a certain speed. So here is my equivalent circuit or rotor equivalent circuit as a function of slip. That's why we introduced the whole concept of slip. It's much easier to talk about things when we include this value of slip. So now I'm going to get completely away from the transformer. And now I'm going to move everything over here onto the primary side, because again, getting that A effective is very difficult. And I'm going to figure out a way to measure the parameters. So everything on the high side of the transformer, everything without worrying about A effective, is going to have my primary side representation. And then I have an X2 and an R2. So those are going to be the impedances that are reflected from the rotor circuit onto the stator circuit. And this is really important to me because this is where I'm applying an AC voltage and an AC current. Before, when I was over here, this is an induced current. That comes in from the power supply, but it's very difficult to tease out. Over here, I can tease out pretty quickly what's going on the rotor and what's going on the stator. Now, this is really an excellent representation because you'll notice that this JX2 is going to be, somehow you're going to have to be given that based on a certain value. So it's A effective time XRO. My R2 here, you'll notice is R2 over S. And let's think about that from a perspective of slip. So let me just make sure I'm recording. I am. So when the machine is completely slipping, what does R2 over S look like? So my slip is equal to 1, right? So it just becomes R2 over 1, which is just R2. So I have gobs and gobs of current going here when my slip is equal to 0. When the machine is just starting up, I've got a lot of current flow initially. Once I start getting up to speed and get closer to synchronous speed, what does S look like? S gets closer and closer to 0, right? So this impedance right here, the R2 over S, starts to look like a really big number. So the current through here looks way smaller when it approaches, I said 1. It should say, oops, this is 1. And this is 0. I had those backwards. So as R2 over S has an impact, because as my slip approaches 0, getting closer and closer to synchronous speed, then what I find is that my current goes way, way down. Until when I get to the slip where there's no slip at all, when they're operating at synchronous speed, at that point, this current has to be equal to 0 because there's no voltage source there, right? There's no relative change in the speed of the magnetic field versus the actual speed of rotation. So there's no changing magnetic field in the rotor, so there's no current flow. Okay, pretty helpful, pretty important idea to understand how these machines work, because we can't come up with an equivalent circuit of our induction machine unless we use the concept of slip. So this is a big change because now we're rotating. We've got something that's changing. So we have to analyze a system based on speed of operation. Transformers, there's no speed of operation. They're stationary. They're not moving. Synchronous machines, if you remember how we did synchronous machines, they have to run at synchronous speed. So we didn't care about the speed characteristics. We just knew it ran at synchronous speed or it was shut down. There was no in the middle. Over here, as we talked about when we looked at this curve here, synchronous machines can operate at essentially any speed. They can operate at no speed, or they can operate at 100% speed or synchronous speed. And as long as the machine is kept cool, you certainly could run that at 200% of its full load torque, but the likelihood of the machine lasting a long period of time is not going to be very good, right? Because the full load torque is down over here. And if I'm running this much torque, what happens? Well, I'm pulling more current through the machine than it's rated, and it's not spinning, so that you don't have the cooling effect of the fan, the blade that's on the rotor shaft that's pulling air through the machine. So the winding tends to get heated up, and you'll actually have a machine that will, if you don't stop it, will catch on fire. Interestingly enough, does anybody know what the NFPA 70 says about how do you protect fire pump motors from conditions like this? You have a NFPA, right? Is a National Fire Protection Agency. So you would think that they'd care about fire stuff. Well, they say the protection on a fire pump should be such that it protects the motor, right? That's what you normally would think. But the NFPA 70 thinks differently. The NFPA 70 says, let it burn. The protection on this is you can run this at locked rotor current, which is the highest current it ever has, for an indefinite period of time. Does that make sense? Depends on your perspective, right? You as the electrical engineer are really worried about your electric motor. You're going to burn that thing up, right? Maybe even catch it on fire. But what are the fire people interested in? We want to put the fire out. So they'll keep that motor running as long as possible because it becomes a life safety issue. So you don't ever trip a fire pump off for running at locked rotor conditions for an extended period of time, because as long as that motor can pump and provide water to run the sprinkler system or to provide hoses to the firefighters, then they would go ahead and do that. Now, I said run it at locked rotor conditions. That does not mean let it run at any current it wants, because if it runs, let's say locked rotor current is 7 times the full load current. So let's say that's 700 amps is what the locked rotor current would be. Would you be okay running it at 10,000 amps? Why not? 700 amps is too much. It wouldn't be the wire. You have a fault in your system, right? So the only way that you're going to have about 700 amps continuously is that something is jamming the fire pump, or maybe it's working really hard to pump water. You don't necessarily know, but it's working extra hard to pump water. But if it's 7 times, it's most likely that the motor is the issue. But if it's 7,000 or even 2,000 amps, it's most likely there's a fault, there's a broken wire or something has come into contact with ground or another phase. That is not the fire pump is causing the issue. It is the electrical system is causing the issue. So you still need to protect that fire pump. You just have to assume that it's going to run at locked rotor conditions indefinitely. So protection is still important because you don't want a 10,000 amp fault or even 2,000 amp fault to exist on a system indefinitely, because then you really have some serious issues. So this is the thing we talk about, some of the application stuff. It's going to be very sensitive because you can get yourself into a lot of trouble by setting up the protection for a plant. And you forget about the fire pump saying, oh, we don't need it. We'll just bolt it into the panel and just let it burn if it needs to, but not the right way to do it. So anyway, this thing can run, no problem here, but maybe not for long. You can go up to pull-out torque, but interestingly enough, you actually draw more current over here than you do with the pull-out torque. So it's outputting more torque. Does that make sense? Does it draw more current? Why does it make sense that you have more starting current than you do at the pull-out value? The trick question.
Inertia?
No, it's not inertia. Anybody want to guess? I've used this example in the past. Go ahead. Brandon, what did you thought?
I was just gonna say, since you're now rotating at your full load, it needs less current to actually keep the rotor moving.
That's kind of what I think what Brazil said, which is inertia, but not quite that. Anybody want to guess? What does power equal? Torque times omega. So as you increase omega, right? So your torque goes up just because it's spinning faster. That's all it is. You're just spinning the thing faster. It's not that you're putting in more current. It's just because the thing is rotating at a higher rate of speed. That's all it is. But over here, there's no speed. To put out 200% torque at essentially no speed, and clearly, this doesn't actually hit the curve at 200%, right? I mean, it's right there. But it has no speed. So if this is basically equal to 0, right? Think about how much power needs to be when this is not contributing anything to the torque, when omega contributes nothing to the torque. So that's why you put way more current in under starting conditions than you do under full load conditions. Question?
Omega the same speed, the speed on it. The x-axis of that graph.
Yep. So the speed over here is much higher than it is over here.
So the speed's higher and the torque's higher. So the power will be higher there.
No, what I'm saying is, if I want to go ahead, so let's just say that this is 450%. Okay, let's say that that's 450%. So what needs to put in more power when I'm running at omega equals 1 or omega equals, let's say, 1500? What has to put in more P? They both have to be equal to 450%. So if I plug in P times 1 equals 450, or P times 1500 equals 450, which P needs to be greater? Way greater, yeah. So it's putting in a lot more power at 1 RPM than it is at 1500 RPM. So the whole reason why I said that is because I want to make sure everybody understands that way more current goes in starting than it does even at the pull-out torque, and it has to do with the fact that you've got no speed. Once you get up to speed, obviously it drops out. And these things actually get way more efficient when they run at higher and higher speeds. So the closer you can get to synchronous speed, the more efficient this machine is. Good question. Okay, so let's break up our losses in the machine. So we have this. So we've got our equivalent circuit. And we've got to go ahead now and do power losses, just like we did in a synchronous machine, because in the induction machine, we've got these mechanical losses that we have to characterize. And somehow we need to add those in or put those in into our system so that we get an equivalent circuit that is valid. So we get stator and rotor copper losses. Those are I squared R losses. Stator copper losses are the ones, the subscripts with 1. The rotor copper losses are the subscripts with 2. We have core loss, because we have a magnetizing core. This is the same thing as in a transformer. This is where we actually start to get a little bit of difference, because now we have mechanical power losses, friction and windage losses. So how does the power flow? Like this. And we have a couple of interesting or different terms. We have a little more specific detail, because we're always going to be talking about this as an induction motor. RP, input power, again, this is real power, is going to be equal to square root of 3 VTIL cosine theta. This here, remember what we said, this is almost always given to you as a line quantity. So that would be the voltages across 2 lines. So you can see this equation is written as terminal voltage. So whenever you see the nameplate terminal rating, the voltage rating on the nameplate of a transformer, an induction machine, that voltage that you see, the 480, the 4160, is a line voltage. A lot of motors are actually dual rated, so you can run them at a couple of different voltages, but those would still be line voltage parameters. All right, so all the power now is coming in is electrical. I got some stator copper losses, and you can follow along pretty well here. So here are my P stator copper losses. First thing that's gone. Then I've got my core losses here. And so at this point, I'm right before I get to my rotor circuit, right? Right before I jump through the air gap. So this is the actual power that goes from the stator to the rotor, and that's the power that you lose in our air gap. All right. This is where we start to deviate quite a bit, because when we talked about in synchronous machine, we only talked about stator copper losses, right? Because the rotor copper losses or the field losses were all DC, so we didn't include those as part of our AC analysis. They would need to be included if you wanted to get the true efficiency of the machine. But we're not worried about that because it's coming from a DC source. We don't have to analyze that. We'll let the DC people take care of that. But now everything is on the rotor. So I've jumped from the stator to the rotor, and I've gone through the air gaps. We call that air gap power. Now I've got a current flow through a winding, and that winding is on the rotor. So I've got my rotor copper losses. And that is, those are right here, or sort of from here. We'll see why that changes a little bit in a second. But our rotor copper losses are there. Now, all the power that needs to go for the electrical system or to make it work electrically is done. We don't have any more losses in electric power. All the losses moving forward are a result of mechanical. So why not call this power our converted power? That's the power that has been converted from electrical to mechanical. And here, because it's mechanical power, we can actually write it as a function of torque, because mechanical engineering folks don't really care about power, especially from a rotating machines perspective. They really care about torque. So this is the induced torque times omega sub n. This is the speed of operation. Now I've got some friction and windage losses. So as we talked about, those are bearings, those are sliding on the shaft. Those are the actual losses because of mechanical losses. And then you have these random losses that you can't characterize. So we'll just count those all together as a mechanical loss, and we call those, or miscellaneous or stray. And then our output power is very close to our converted power. Actually, not necessarily really, but can be somewhat close. And now that is our actual power that is available to drive a load. Or that power is driving a load. Because if you have no load there, you don't have any load torque, right? So you have to actually have a mechanical load on it. Now, typically, because electric motors are far more efficient, 92, 93%, you don't lose a lot. You can play games And some people do, like they try to get what they call premium efficiency motors. And premium efficiency motors basically are really smooth shafts, so you can actually polish the shafts. So if you have a really fine polish, it makes it slippery, right? If it looks like a mirror. Well, the other idea too is if you take paint and you sand it down with a really fine sandpaper, you can make almost a flat plate become gloss because you just smooth it down to those, have almost no imperfections. So that's very slippery in the wind, but also you can get fancy bearings. So you can get really fancy bearings that are just ball bearings with really fancy grease. And ball bearings are all manufactured, but you can actually have shiny, well, all ball bearings are, but the reason why they're shiny is because those are polished ball bearings. And you can actually spend more time polishing them to make them even smoother, make them perfectly round so that you have less friction. You can also use fancier grease. You can use, I don't know, I'm not a lubricious technician or whatever. I don't know much about lubricity, but you can use all kinds of synthetic oils and stuff like that that can run at high temperatures that can be very efficient. I worked on a project this many years ago in the Navy. They were using magnetically levitated bearings. So they would put a shaft and they would magnetically levitate it, and then it would just spin in the air. And it had to be kept in a really tight position because that's what bearings do, right? They keep the shaft from moving in all different directions. So they had to have magnetic fields located around it, but they actually magnetically levitated the bearings so that you would have no friction. The real reason why they did that is because these are on Navy submarines. So one of the ways you can check for submarines in the water is the bearings when they hit the shafts, that hits the propeller and that vibrates, and you can look for the noise in the water based on the vibrations of the propeller. So if it's suspended in the air, there's no physical contact, you've got no vibrations. It doesn't really work that way. So, but yeah, that's how you can get these things. And it's pretty common for these to be pretty darn efficient, 92%, 93% efficient. You can even get higher levels of efficiency. Where you start getting higher levels of efficiency, there's only so many things you can do to improve the mechanical characteristics of it. I mean, you can't get something for nothing. So now you got to start using fancier, bigger wires. So having much bigger copper wires will improve the efficiency of the machine. Also, if you can keep the machine cool, so if you can improve the ventilation, that's another way that you can get it. So some of the premium efficiency motors, if you look at them, they have big fins on them. What's another thing to say a fin? Just a heat sink, just a hunk of metal that sticks out in the air, and it provides a larger path to conduct heat to go through that. So we'll learn more about motors, but the most efficient motor is what is called, and it's a type of enclosure, but it's called an open motor, open enclosure motor that is quote unquote drip proof. So it has a case around it. So if water's dripping on it, water shouldn't get in the shaft, but it's open on each end, kind of like the motors that we have in class. And the reason why it's open in each end is you can have a fan blowing and pulling air in to help and running over the windings to help keep it cool. Only works in certain applications. If you're in a mill processing area and there's water sloshing around and dirty fibers everywhere, that stuff gets sucked into the motor and it makes the motor dirty and it kills the efficiency of the motor. So those are called enclosed or totally enclosed or explosion proof. There's no external air that's allowed to go in. And those motors run very hot because there's no air exchange. All the heat exchange happens through the fins. Okay, so let's do a few equations. Our PN, I should say, is VI cosine theta. Don't forget you need to have the 3 or the square root of 3, depending if you're using line voltages and currents or phase voltages and currents. Stator copper losses. Hopefully by this point in the semester, we love I squared R. We can't use the voltage V squared over R because we don't know what the voltage drops are. Now we've got to start looking at our diagram here, and we say that here's our air gap power. We can see clearly our air gap power is going to be equal to our input power minus any stator copper losses and any core losses, right? So we specify that here. Then our rotor copper losses is again I squared R. Now our converted power losses is we take the air gap and we subtract rotor copper losses. And that's our converted power. Oops. And then our output power is going to be our converted power, right? Minus any of the friction and stray losses. So we can use this and we can see that our induced torque is our P converted over omega sub m. How do I get air gap power over omega sub sink? Any thoughts? Well, what is the equation for omega sub sink? Isn't that equal to, or actually, well, I want to say it this way. Let me make it this, it's a little easier this way. Omega sub m is equal to 1 minus the slip times omega sink, right? Our slip speed is that ratio, so we can pull out omega sub m, so we can solve for omega sub sink equals omega sub m divided by 1 minus s. Or we can just use this and substitute that into here. And now, so we have T induced is equal to P converted divided by my synchronous speed times 1 minus s. But these two equations aren't the same. Well, what we'll see is our air gap power. We're going to be able to calculate that. And I have that here in, I think, a couple slides. Our air gap power is going to be equal to our converted power, sorry. It's going to be equal to P air gap times 1 minus S. So when I stuff that into here, then this becomes T induced equals P air gap times 1 minus S over omega sink times 1 minus S. So you can see that 1 minus S cancels out on the numerator and the denominator. So one of the things we need to think about is what is happening to our rotor copper loss. That's a function of the slip speed. And we'll see how we can break the R2 over S, and we'll do that right here. We're going to break R2 over S into two separate parts. We want to break it into an R2 and an R2 times 1 minus S over S. So how do we do that? How do we get there from here? So remember, we have R2 over S. Maybe I'll ask it as a question. Does R2 over S equal R2 plus R2 times 1 minus S over S? Is that correct? Because what I'm saying is these two right here should be equivalent to R2 over S. If they're not equivalent, then we just modified our equivalent circuit. Well, let's do a little bit of math. So common denominator of S, this becomes R2 times S. We'll move this down over here, plus R2 times 1 minus S. That becomes all over S. You can see that this R2 over S and this 1 cancels out. And so now, wait a minute. No, I'm sorry. Let me do that again. So let me just expand it out. So I'm running out of space. So this is S all over S. So this is going to be equal to S times R2 plus R2 minus R2 times S all over S. That and that cancels. So does R2 over S equal R2 over S? Yeah. So why did I break these up? Because that's P rotor copper loss, right? That's just I squared times R. That's the power consumed in the rotor copper loss. And what is this right here? That's my converted power. That's the actual equivalent resistor to calculate what the output power that motor is providing. So we've now broken it up in terms of two resistors, because electrically speaking, we need to figure out how our output power, which is mechanical, how that output power, that converted mechanical power, is equivalent to a resistor so that we can do our circuit analysis. We can't just keep it as a torque. We somehow have to bring that back in and treat it as a resistor, inductor, or capacitor. And so that some R value we talked about for a rotor resistance, that is a pseudo rotor resistance. It's not the real rotor resistance. It's the rotor resistance plus any output power that we have. That is our converted power. So you can use either one. You can use this one, R2 over S, or you can use the R2 and the R2 times 1 minus S over S. It just depends on what you're trying to calculate. Okay? If you're trying to do the conversion stuff, it sometimes is easier just to do it with the circuit shown here. But this circuit and this circuit are exactly the same in terms of the voltage and the current seen by the source. There's no difference between those two. So now we can do our equations. This equation doesn't change. Check, check. This equation is the same. But now what we see, so let's go back up to our diagram. So we can see that our air gap power here, we said it's equal to P in minus these two. Isn't it also equal to our converted power plus our rotor copper loss? We can go from left to right or right to left. They should be the equivalent to each other. So that's what this is. And what we see is if we use our equivalent circuit where everything is R2 over S, correct? Then what we see that this power, the power that is consumed in the rotor circuit plus the output power is just going to be equal to that current flow through that resistor, I squared R times 3. So that's that equation over here. But remember, the I squared R losses in the rotor are just these two. So this is the rotor copper loss. So I can substitute that back in and end up with just P rotor copper loss divided by S. So now I'm going to go ahead and do my P converted. My P converted is equal to my air gap power minus my rotor copper loss. So this again is just combining these two. So I have 3 I squared R times 1 minus S divided by S. And again, if that looks confusing to you, let's see. So my air gap power is, did anybody need me to see where I got that? Would that be helpful to see how I got that? Let's just do it so that there's no confusion. So P air gap is equal to 3 I squared R2 over S, and P rotor copper loss, sorry, is equal to 3 I squared R2. So now I'm going to put these together and add those together. So I have 3 I2 R2 over S plus 3 I2 squared times R2. How can I combine those? Well, I can do some factor, or actually it's minus, not adding, sorry. So this is minus. So now what I need to do is do a common denominator. Let me move this to whiteboard. So, because I'm really running out of space. So it's 3 I2 squared R2 all over S minus 3 I2 squared R2. This is the air gap power, right? This is P converted minus P rotor copper loss. Those are equal to each other. So now I'm going to put them under a common denominator. Here's my S term, all over S. Now I can factor out 3I squared 2 R2. So then what I'm left with is 1 minus S all over S. That's just the algebra to get there from here. That's this equation over here. Yes, sir.
What is I2 and I2 talk about?
If you go back to the equivalent circuit, I2 is the current flowing in the equivalent rotor circuit. So that's reflected over. And R2 is the actual rotor impedance, the resistance, I should say. That's the actual, you can measure that. If you could measure it directly, you'd measure 2 ohms or whatever. So you get that from the equivalent circuit. Okay, so now my converted power, if I take a look at this, well, my air gap power is my rotor copper loss divided by S. I just have that remaining term. So that's my converted power, 1 minus S times my air gap. And then I can go ahead and I can substitute again for my P out. So that's P converted divided by P omega. Well, P converted is here. And we already divide omega sub S. So those terms will cancel. So either one of those will work. You can use the air gap power divided by omega sub S, or you can use the converted power divided by omega sub S. All right, just a lot of equations to go ahead and do that. But why is this important to us? Can you look at this diagram and tell me why this is important? There's something really important in here. I have 1 unit of air gap power going in. What's coming out? I have some rotor copper losses and some converted power. What goes out as the power, the actual converted power is 1 minus S. What gets eaten up by the rotor copper losses is a function of S. Do you remember maybe 30 minutes ago when I said, how do you want to operate these machines? As close to synchronous speed as possible. Why is that? Because as close to synchronous speed as possible means S equals 0. If this is 0, how much rotor copper loss will I have? How much converted power will I have? All of it. So when you build an induction machine, you want to run it as close as you can to synchronous speed because it runs more efficiently. More power gets converted to torque and less is wasted on generating heat in the rotor circuit. So this is the biggest reason why, or this hopefully helps you see why it is essential for us to run a motor at as close to synchronous speed as possible. It's so important. Let's see if we can go buy a motor. Let's see if we can buy one. All right. Here, how about a WEG? All right, so blah, blah, blah. All right, can you tell me anything about this machine based on this data that you have here? Kill this. Maybe we can see the whole kit and caboodle. I'll scroll up a little bit. Oh, I can't scroll up. A lot of information, right? But this is when you buy a motor, this is what you buy. Or this is what you need to get. You need to look at it. I'm really interested in, let's see if I can annotate that. Why is that so interesting to me? Because this tells me, and you got to read it carefully, that this machine has a rated speed of almost 1190 RPM. That's when it puts out 100 horsepower. It puts out more than 100 horsepower at less than that. But it's not going to last very long unless you have really good cooling to be able to provide that. So this is running at 1189 RPM. Look at the slip speed. Look at the slip of me. It's less than 1%. This is running almost at synchronous speed. So what that tells me is that this machine, can you calculate omega sub S? Remember, omega sub M is equal to 1 minus S times sync speed, right? So omega sync is equal to omega sub M divided by 1 minus S, which is 1189 divided by 1 minus 0.92%. So 0.0092. What is that number equal to?
Pretty much loading,
It should be not 1189, it should be higher than that.
Yeah, 1200.
1200 RPM. Do you remember when we looked back and we looked at synchronous machines? And we said the speed of operation is determined by the number of pole pairs. If it's a 2-pole machine, it was 3600 RPM. A 4-pole machine, 1800 RPM. What did we say about a 6-pole machine? 1200 RPM. So this is almost at synchronous speed. It's only 11 RPM away from being at synchronous speed. So if you go back to this right here, this actually, maybe is way, way, way down over here at the extreme limit of what that machine will operate at. And that's where you get the highest levels of efficiency. So if I go back to that nameplate, and this is a premium efficiency motor. So what is the full load efficiency on here? It says premium, but it doesn't actually tell you what that is. Oh, another important, yes, sir.
wrote that, the 1189 over 1 minus 0092.
Yep.
Why did you write 0.0092 and not, point, 02 for this slope?
0.02 or 0.92?
Why didn't you write it as what the slope is?
I did.
I thought the slope was point. Oh, that's 0.92. I thought it was 0.02.
No, it's 0.92. No, that's okay. The other thing too, remember we talked about number of poles? Look right here. It even tells it's a 6-pole machine. We did the calculations. We're so smart. We didn't even need that data sheet to figure that out. But it doesn't tell us. It tells you super premium efficiency. Oh, here we go. Okay. So I'm assuming that when this thing operates at 100% nameplate, so 100 horsepower, this is running 95% efficient. Go talk to your mechanical engineering friends and see if there's anything that they have that is operating at 95% efficient. What does your car operate at? Your combustion engine cycle? 25? Can you see why EVs, even though, they're not as sexy as they were a year or two ago, can you see why EVs eat for lunch carbon-fired vehicles? You just can't keep up with efficiency. You can have the most elegant design, turbocharged, direct injection, supercharged, intercooler, whatever version you're going to get, and you just physically can't match the efficiency. There's just no way they're going to do it. And the conversions from electrons into the chemical energy are much better than the thermal conversions. It's just that the battery technology is not there yet, right? That's why EVs haven't taken off. Anybody here, would you buy a car that you can get, I think like a Tesla gets 100 miles per gallon is the equivalent, but you can only go 360 miles, right? What if you could go 1,000 miles and it takes 30 seconds or 60 seconds to recharge? You'd think differently about, whether you'd want because it's the range. The concern is I'm really nervous about range. So if I'm driving someplace, I don't want to have my, Tesla, because they have all the charging stations and they're really smart about locating them. But it's it's a good for the initial market foray, but in 10 years maybe, or even 20 years, is the supercharging network going to be as important? You'll have to have them spread out, but you won't have to have them at 300 miles. Like right now, amazingly enough, there's one in Waterville and then there's one in Augusta. It's 15 minutes away, 15 miles away. Why would you need to have a supercharger that close? They'll spread them up further, especially if you can get range. I think it's called range anxiety. I'm just going to run out of gas, quote unquote, and I can't get there from here. So something to think about. But anyway, 95% efficient is pretty darn good. In my opinion, you may disagree. All right, let's do an example. Whole lot of information now. Now we really start getting detailed long problems. So I know we like to be as efficient as possible, but there's not much we can do because we just need the details. So 480, 60 hertz, 50 horsepower, 3-phase, draws 60 amps at a 0.8 power factor, has stator copper losses of 2 kilowatts, rotor copper losses of 700 watt, friction and winch losses of 600 watt, core losses of 1800 watts, and stray losses are negligible. Take a breath there, right? So the first thing is what's relevant and what's not relevant. Well, I don't really need 480 because I'm not calculating any current here. I don't really need to calculate. I don't need that for anything because I'm not looking at speed. What about 50 horsepower? Do I need the 50 horsepower? What's that?
Yeah.
Yes? The answer is no. That's the nameplate rating of the motor. That's what it's capable of providing. Does that mean it actually is providing 50 horsepower? No. Most of the time, when we looked at this nameplate over here, what is the likelihood of this thing being operated at 100 horsepower? Almost nil. You buy a motor, let's say it's 100 horsepower, but your mechanical engineering friends have said, I need 96.2 horsepower at, let's say 1780 RPM. So you're like, okay, I'm just going to buy a 100 horsepower motor. I'm not going to design a custom 96.2 horsepower for that application. I'll just buy 100 horsepower and it's going to run a little bit faster than it needs to because that curve, remember that curve that we do, maybe it's over here is what the mechanical engineer designed it for, but you don't need that much power, so you operate over here, which is not a problem because you have to design a custom motor. It's going to cost you way more than buying one off the shelf, or quote unquote off the shelf, and you're actually more efficient. So what's the problem? As long as you have the space for it, you go for it. All right, so we don't really need the 50 horsepower. We definitely need the current and the voltage. And I guess technically, we do need this right here because we will need to calculate P, so I misspoke. So we definitely need 2 kilowatts. We need that, and we need that. So all you need to do this problem is go here. You have P in. You start subtracting all those terms, and you get your answer. I have it over here, but I just wanted to show you where I got these equations from. So my input power is square root of 3 VI. Yes, sir.
It's still relevant if it's a delta Y.
It is, but keep in mind, because I'm using V line and I line here, that's what it takes out whether it's delta or Y. If I'm calculating equivalent circuits, then I start to have to be careful about delta or Y. But I'm just calculating power losses here and power in the machine. All I need is 3-phase quantities. So that's why I use V line and I line. I don't really care because they clean each other up, if you will. Okay. I still need the square root of 3. Yep, because it's V line times I line. If I did V phase times I phase, then I'd have to start monkeying with both quantities to make sure I've got the right voltage, and then I would multiply by 3. But if you use the square root of 3, usually you can just plug and chuck, makes it much easier. So the input power to this machine is 42.4 kilowatts. Here's my air gap. Go back to the power flow diagram for an induction machine, and I have to drop my stator copper losses and my core losses, and that's the actual power that jumps across the air gap, 38.6. Now my converted power is I take my air gap power and I subtract from that my rotor copper losses, and this is the equivalent power to what the mechanical torque would be, 37.9. Now I got to start dumping out any friction and windage losses and any stray losses that are there. So I take out my stray losses or friction and windage losses. Now I'm down to 37.3. And interestingly enough, remember how I said I didn't need that 50 horsepower? It just so happens, though, that that happens to be 50 horsepower when it's drawing 60 amps. That's coincidence. Doesn't actually have to draw 50 horsepower. It's just that operating at 60 amps gives you that. And then finally, the efficiency of this machine, P out over P in. I put out 37.3. This is mechanical torque. My input was 42.4, 88% efficient, which I would call that average efficiency for an induction machine. Doesn't have to be elegant, just average typical efficiency. Okay. Questions on doing induction motor calculations? Because we went through the test, we want to see specifics. So that's why I was bouncing around a lot, going up and down. Hopefully that doesn't cause any confusions. But where did I get these equations? I got these equations from our power flow diagram. The equivalent circuit, we just stole it from the transformer. So the same concepts in the transformer. When we have magnetizing losses, we have this and that. So if you want to understand and have a deeper understanding of an induction machine and where the losses come from, you can go back into that. But we'll use this for our equivalent circuit. We'll actually see we can actually do very similar tests to the transformer. Remember, we call them load loss and no load loss test. Right? So load loss and no load test maybe is a better way to say it. We're going to have to come up with similar tests for the induction machine to be able to obtain the parameters. Questions on induction machines, because they are incredibly important to the industry of the world. Yes, sir.
I'm having trouble with comparing the motor with the transformer comparison.
Yep.
At toward the beginning of the slideshow, you have a full equivalent sort of.
Of the motor, yep.
Yeah. So is that the left side would be the rotor? Yeah, left side would be rotor, right side would be the stator.
Opposite. The left side would be the stator and the right side would be the rotor. Hopefully my right and your right are the same. Let me go back up and look. Here. So this is the equivalent of the stator. This is where the power is coming in. And this is where the power is being delivered to the rotor. And you can see the rotor is short circuited, just like the windings are in the machine. Yes, sir.
You really use the current ratio on say, or you put it down on level?
We really can't because it has so much to do with speed. So it'd be very difficult to do it. So we oftentimes just ignore it. Or we come up with a value that operates for a typical operating range of the machine. And we don't worry about it. There's too many things happening to be able to calculate it. You really need to do really in-depth magnetic material analysis to make it make sense.
Mm-hmm.
Everybody heard what happened, was it Tuesday morning in Baltimore with the bridge that happened? So some of the stuff, because I follow these random blogs, some of the things that they're talking about is they should have backup power. They should have backups. They should have backups. Well, the backups on those, how do you lose propulsion? You've only got one propulsion system. And so what they're talking about doing is we should have electric driven motors as a backup. Maybe you can't provide the full oomph that that I would imagine that those are diesel engines, maybe that run those. But you don't have the same oomph that is there. But in the event of failure, you can actually still maintain propulsion. That's what Navy submarines do. Navy ships do. Because if you lose power on a Navy submarine or a Navy ship, you're quote unquote dead in the water, right? You can't just sit there. So what they do is if they lose propulsion, like the steam, the reactors go out of business for one reason or another, they have batteries on there, DC batteries with some sort of, I don't know the size of the motor. I probably couldn't tell you anyway if I knew it, but I don't know what it is. And they will run the propulsion, the main propulsion will be driven by an electric motor, not the speed, not the time, but the thought is it'll try to get you out of harm's way. So maybe 8 or 10 hours to get out of harm's way, and then maybe you can do a distress call. But at the very least, you can get out of there. And I don't know about these ships and all that stuff. Everything is built, so fast and cheap that maybe they just figured, it's not that much of a reliability issue. Because what happens if you lose ship's power or propulsion power when you're out to sea? Unless you're in a storm, you just call somebody and have you towed someplace, right? But we saw in that case, you lost power in a quote unquote dangerous zone and crash into a bridge, which is going to cost billions and billions of dollars when all is said and done. Yes, sir.
Do you have to, like for a backup electric motor, do you have to be connected to the same shaft as the diesel motor?
Yep. Yep.
So with the electric, like if you lose the diesel motor, the electric motor would then have to spin the dead diesel motor?
No, you can decouple the motor. Or you can have, it would have to be like a transmission, right? And the diesel engines might run at 1800 RPM, which would be probably too fast for the shaft. So they probably have some sort of transmission system that works there. I don't know. I'm not a ship's person. If they did have that, you would have to somehow figure out a way to decouple. So if it was a hard connection, you'd have to decouple it. But there's one way that you can do it. So most of the time, anybody ever try to turn over your engine, your engine yourself? It's really hard because there's compression. So if you had a way of removing the compression, then it's really easy. So if you could somehow open up those piston heads so that the compression are just going in and out really easily, it's not that hard to turn them because, the pistons themselves are really tight within the cylinders, but it's got oil in it. So it looks tight, but actually, if you didn't have to worry about compression, you can usually spin them by hand. It's just when you've got the head on and you've got gaskets and no air is coming in or out except through this valve system, now you're compressing air. So that's what hard work is. So if you had a way of making it so that you wouldn't have to worry about that, you could do that. Again, this is pie in the sky stuff. It might not ever happen, but if you have accidents like these, what do you do? Sometimes you overreact and then you put more stuff in it than is necessary. But it just depends on how important the application is, right? If this was the same example we talked about a building with fire pumps, they would figure that out. So maybe this one accident's not a big enough deal to make changes. I mean, ask the people of Baltimore. They might think, I lived in Baltimore for 6 months, so I've been on this bridge many, many times. And yeah, it's a little bit of an interesting experience there. But so they'll have to figure out backups. I mean, usually they have a couple of generators and maybe that's what they thought, but maybe one of the generators was out of service for one reason or another. It's unlikely that if you have multiple generators, all of them are, multiple engines, that they'd be all out of service, but I don't know. Locomotives, does anybody know how a local train works? Yeah, it's diesel that runs a generator that drives an electric motor because you have way better speed control.
Probably lost power, they regained the power for a bit, then lost it again.
Yeah. Yeah, not a good thing. All right. Any questions? Feel good to get back in material because last few classes were test, review test, go over test. Because this is like the last major important topic that we need to cover because most of you all, when you work in industry, you will have to work with induction machines. So this is an important one for us to be able to understand. Nothing else? Okay. Have a great day, y'all, and I will see you on Monday for lab. Take care, everyone.
Thank you. You too, John. You too, Paul.
Thanks.